Okay. So now I'm going to do the powers of the 10. Times 10 to the 7th on the top, right? 10 to the 7th times 10 to the power 7 divided by 130 million squared. 130, boom, 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 squared. Oh, very weak. That's the maximum gravity. 1.216 times 10 to the minus 8 meters per second squared. So this test is going to have lots of integration, lots of calculations. You got to be practice that calculator, practice the hell out of that calculator. Okay. So you don't want to make a mistake in these kind of calculations, just a silly mistake, you know. Okay, so a 200-pound person would weigh what? Well, then you just take the ratio. 200-pound person times 1.216 times 10 to the minus 8 over 9.8. Because they are 200 pounds on the Earth's surface. So over there they would weigh how much? Well, then it's just a simple ratio. This meter per second squared over 9.8 meters per second squared. So they're going to weigh almost nothing. So divided by 9.8 times 200. 2.5 times 10 to the minus 7 pounds. And that's the maximum you're going to weigh from that. So that means the ring of Saturn is not going to have too much of an effect on the person. It's too light. Mainly the Saturn itself will have an effect. But if you are heavy to begin with, then the force you feel is stronger. You know? So it's not going to have too much of an effect on us. Okay. But now if you notice back to that page, the ring of Saturn is not a true ring. It has an inner radius and it has an outer radius. Right? You go back to the A ring, 122,000 to 136,000. So truly, what is it? It's actually a plate with a hole in it, a cylindrical plate. A ring is just assuming that it has no thickness. Right? So how do we find the gravity of a plate? Maybe that has an inner radius and an outer radius. Monday, so one of you guys might be working in JPL to model the gravity of planets, rings, and all of that one day, right? So plates, something like this. R1, R2. So we can take the whole A ring, or if we want, we can take the whole set of rings of Saturn, combine them from the inner ring all the way to the outer ring, right? And then make a plate out of it. So what would be the equation for that? Well, we already have the equation for a thin ring, so we can model a plate as a bunch of thin rings, right? So we say a plate is made up of a ring right? What would be the gravity created by one of those rings? dg by a ring is what? It's going to be g, the mass of that ring, the mass of the ring, times what? X being the distance from here to here, over the what? Over the radius of that one ring. So I'll put it as little r. See? So over the radius of that ring squared plus the x squared to the 3/2. Okay, now we introduce something known as surface mass density, sigma, which is dm over dA. So that gives you the ratio of the mass of that ring to its area, right? Ratio of the mass of it to its area. So this has a certain area dA. Then I'm going to say dm is going to be sigma dA, and dA is going to be what? 2 pi r dr. The circumference of that ring times the thickness of that ring, right? So we do this in physics 3 also with charged plates. Right? Then you're going to take this and put it into here, dg ring, g sigma 2 pi r dr x over r squared plus x squared to the 3/2 power. Then now this is integrable. I'm going to integrate this from what? From the radius of the inner ring to the radius of the outer ring, r1 to r2. Okay, so g is going to be what? Well, now I can factor out anything that's constant. So 2 pi is constant. Sigma, I'm assuming, is constant. That's the mass density of the ring. So I think for rings of planets, their mass density is probably constant. Well, that one does seem thinner. But this one throughout the A ring seems like it's constant. So that one is going to be 2 pi sigma g. X is also constant, which is the distance from here to here. So as you go to further rings, the x is not changing, it's staying the same. So then you got x, then you got here integral r1 to r2, r dr over r squared plus x squared to the 3/2. So what are we integrating over? We're integrating over all the rings with radius little r, and then their thickness is dr. Is that an integral that I can do without looking at the table? Yeah, because it's a simple, I think it's a simple substitution. Let u equal r squared plus x squared, du is going to be 2r dr, r dr is going to be du over 2. So then I could just do du over 2, u to the 3/2, right? And then what is the integral of that? U to the minus 3/2, and then you add one, u to the minus half over minus half, right? So it becomes u to the minus half over minus half times 1/2, which is this guy. So that cancels. So then the final answer is just 2 pi g sigma x minus 1 over r squared plus x squared to the 1/2. Because since it's negative half, I brought it back down to the bottom. Then I go from r1 to r2. So then you have g of x 2 pi g sigma x. Then I can change the order of the integral. The minus makes the order r2 to r1. So then you put the r1 first. Okay, that's it, I think. Yeah. R1 squared plus x squared minus 1 over r2 squared plus x squared to the 1/2, and then 2 pi g sigma. One other thing we need to do is get rid of the sigma. Sigma is the surface mass density, so it's going to be the mass of the planet divided by its surface area. Okay, so what is the surface area here? The surface area of this guy, right? So it's going to be pi times r2 squared minus r1 squared. That's the surface area of the planet. If it's a ring plate, right? So then we substitute that over there. G of x 2 pi g sigma is m over pi r2 squared minus r1 squared x 1 over r1 squared plus x squared to the 1/2 and then all that's left is maybe get rid of the pi. I think that's it. We can't really simplify it too much more. So this will be the gravity of a plate with an inner radius and an outer radius. Now I can say, okay, what is the gravity of the A ring if it has that inner radius and outer radius? So again, of course, it depends what the x is. This one, is not really clear what the x that maximizes the g will be. We probably have to take the derivative of this again, set it equal to 0, find what value of x maximizes it. But let's just forget that step. Let's just give you the x. And let's do it the same x that we had before. At x equals to r over root 2, but then the r that I used before was the average r, right? So I said 130,000. So let's do it at that same x value. And x equals 130 million meters over root 2. What is g of x? So we'll do it at that same distance, right? But then we'll do it with the actual plate. So 2 times 6.674 times 10 to the minus 11. Then we'll put the mass, which I estimated at 8 times 10 to the 18. Then the x will put 130 million over root 2. Okay, now r2 squared, now I'm going to use this value. 136,775, right? 136,775, but then add 3 more zeros to it, squared, minus 122,000, 170, 000 squared, then all times 1 over, then I'm going to do r1 squared, which is the smaller one, right? This guy. Plus the x squared, so this guy squared, over, then when you square this, you get this squared over 2, right? To the 1/2 power. Oh my gosh, so many things. Minus 1 over the outer radius, which is 130 775 squared minus, no, not minus, plus, yes, plus 130 over 2 to the 1/2. Woo! Now practice that on your calculator. Put it in. That one I'm not going to try to do it on the computer one. I'll use this one, which is better and faster. So see if you get the same answer as what I get. Let's all check it. .2263 times 10 to the minus 8. else got that? No? You didn't get it? No calculator? No, this is your sword. This is your battle sword. You gotta go with the warfare. You gotta have this. Muskets, right? This is our musket, our cannon. Got it? No? What was the gravitational field if we assumed the mass was all concentrated at that radius of 130,000? What was the G for the previous problem? What was it? 1 point G for a ring, 1.25. One six times 10 to the minus 8 meters per second squared. We can kind of say if my answer makes sense or not. That way, you know. This one is coming out slightly larger. So now we took that mass that we had assumed had just one radius. We spread out that mass over a wider area. And then we found the gravity at that same point to be stronger slightly. You see what I did? So I took that ring and I extended it over a wider area. So does that make sense? Should it be stronger? So imagine like this, a ring with a certain mass, the gravity here, versus now I take that and I extend it over a wider range. And now I say, what's the gravity there? Should it be stronger? No? Yeah? Why, Luis? Or anyone else? Why do you say yeah? So now if I'm here, am I closer to the inner side of it? Because if I extended that ring over an area, right, I'm closer to the inner, but I'm also farther from the outer, right? But I think the fact that I'm closer to the inner beats the I'm farther from the outer end. So if I keep extending it and making the ring wider, right? Spread out that mass, and let's say even fill the hole in. What should happen to the gravity? It should be stronger. Well, think about it from a gravitational field structure point of view. With the ring, the gravity field looks like this, right? So here's the strongest. Now if I extend that ring into a plate, what happens? What does the gravitational field look like? Well, it doesn't come down anymore. It just literally goes like this. You see? So now if I find the gravitational field here, which one is stronger? This one, it has to kind of come down and go up. Here it already starts very concentrated, right? It just goes straight and then starts bending with a plate, you see? So it kind of makes sense this should be slightly stronger. Then here it's kind of more open, you know? So the concentration is not as much as here. So I probably drew this wrong. See? So if you take the same location here, this is more concentration. Yeah, so my answer makes sense. Slightly stronger than for the ring. Okay, so then on Wednesday I'll do spheres, gravity inside of spheres. Then we're gonna do the potential energy of planets and stars. Potential energy, and then talk about escape velocity. Escape velocity, and then we'll do different kinds of problems after that. Okay, good stuff, man. This chapter is quite extensive. Lot of material. So keep reviewing it, studying it.